water tank with a radius of 8 feet and a height of 10 feet is being drained at a rate of 5 cubic feet per minute. The formula for the volume of a cone is V equals pi over 3 r squared times height. I can tell you that there's no guarantee that AP gives us these formulas, but they usually give us this formula. If they have cone, if you have like volume of a sphere, surface area of a sphere, 3D figures they usually give you the formulas for unless it's a cube. They don't usually give you the formulas for a cube because all the sides are the same, so you should be able to figure that out. Now I will warn you that on your test, you may see something where it's asking about things like area of a 2D figure, particularly triangles or circles, and it's not going to give you the formula for those. So make sure you know area of a circle, pi r squared. Did I put a circumference problem on there? I can't remember if I put a problem that involves circumference, but circumference is 2 pi times radius, area for circles. Area is pi r squared. You want to make sure that you know those things. I can't remember if you need to know circumference specifically, but they will not give you formulas for things like that. So you want to make sure you know those. 3D figures, other than cubes, they usually give you the formula for that. All right, so the height, if the height of the water level is h, and the radius of the surface of the water is r, write an equation that gives the volume of the water remaining in the tank in terms of h. What does that mean in terms of h? Okay, and specifically, it actually is not even asking for dHdt here because it doesn't say anything about rates yet. That's going to come up, but it's going to be in Part B. A lot of times I see students work out basically all of, in Part A, they do the whole problem and then realize in B that it wasn't asking for that until then. But you can just circle it and draw an arrow down to B if you do that. In terms of H means only an H in the equation. That means you're getting rid of the R in the equation. So we've got our volume formulas given to us, and in this particular case we know we've got a conical tank and its radius is 8, its height is 10. So then our water level here would have a radius of r and a height of h. So we've done some of these cone problems before. This is where you've got to set up a proportion because that r and h is going to be proportional to the bigger cone. So r over h equals 8 over 10. We can cross multiply. 10r equals 8h. Which variable do we need to solve for? R, because we need to replace r. So we're going to divide by 10. So r equals 4/5 times h, or 4h over 5, whichever way you want to write that. So now that we have this solved for r, we can plug this in for r. So volume is going to equal pi over 3 times 4/5 h squared times h. This is all it's asking for in Part A. You could stop here. You would be done. Now, I am going to go just a little bit further because you're going to have to do this either in Part A or Part B. I'm going to simplify this so that it makes it easier to take the derivative. You can do it up here in Part A, or you could do it in Part B. It doesn't matter. You could stop at this point, and you've got the answer. But if we do go ahead and square this, we got pi over 3 And that's going to be 16 over 25 h squared times h. And so that's going to give us the volume formula of 16 pi over 75 h to the third. I don't think it's going to simplify right now. When we take the derivative, it'll simplify a little bit. Okay, questions so far? All right, now part B says find the rate at which the height of the water is changing at h equals 6, include units. So the rate at which the height of the water is changing. What's it asking for? Find dH dt when h equals 6 is what it's asking us to do. So we are going to take the derivative of this equation that we had in part A. So dV dt is going to equal 16 pi over, 16 pi over 75 is our coefficient. We're going to multiply it by 3h squared. And that 3 is like a 3 over 1. And then we also need a dH dt over here. You could multiply, or I would just reduce this and make that a 25. And so dV dt is 16 pi over 25 h squared dH dt. All right, we've got our derivative. We're wanting to find the h dt, so we're not replacing this because that's what we're looking for. We know that h is 6. What else? We need dV dt. What is it? It is negative 5. Very good. So we got negative 5. And you don't have to use the units here. You can if you want. It's cubic feet per minute equals 16 pi over 25. And then you've got 6 feet squared dH dt. And while this could be done without a calculator, and there's a chance it could end up on calculator inactive, this one, because of the second part, ends up being calculator active, so let's use our calculator for this. You cannot until it's solved for dH dt. So you got to have dH dt by itself. So you could leave it, negative 5 divided by 16 pi over 25 times 6. Well, 6 squared. But I would worry about getting everything right on that. So I would just go ahead and do some decimals here because it just is a little bit easier to write out. So we've got 16 pi over 25 times 6 squared. And let's hit that green button before we hit enter. I mean, you can do it that way also, but 72.3823. And that would be feet squared times dH dt. You would need to divide 72.3823 negative 5 divided by that answer is going to give us negative 0.069. And you're doing feet cubed per minute divided by feet squared, dividing fractions, easy as pie. Flip the second and multiply. The square feet, 2 of those are going to cancel. You'll just have feet per minute. And that is your DH. DT. So this would be your answer here. You do not have to use units as you work out the problem like a physics teacher would make you do. You can just wait till the end. You're talking about DH, DT. Height is measured in feet. Time is measured in minutes. So you could do feet per minute. Usually when I work these out, I don't include units as I do the problem. I just think about it at the end. I've been trying to put units in more just because I know if you take physics, you're probably going to run into it more, and it's good to see it a little before you get there. But this is our answer here. We're okay here? Okay, I don't think we've done one like C. Liquid being drained from the tank is spilling into a cylindrical waste basin that collects wastewater. The waste basin has a height of 5 feet and a radius of 7 feet. As the liquid drains from the conical tank into the cylindrical waste basin, at what rate is the height of the water in the waste basin changing? The volume of a cylinder is given by pi r squared times height. So now we have a cylindrical waste bin, and it has a height of 5 feet and a radius of 7 feet. And so as the cone drains, the waste basin is filling up. So let's think about the cylinder. As it fills up, does the radius change? It doesn't. With a cone, it does, right? Because the cone gets smaller towards the bottom, so the radius is changing. But with the cylinder, as this fills up, that radius is staying the same. So the radius here is 7. It's not changing, so we can plug it into the formula. Now, the height, of course, of that water would be changing as we fill up. So our volume formula for this is actually going to be much easier than a cone because your radius is not changing. So you can do pi times 7 squared times height, which is going to give you 49 pi times height. And so if the question is saying, says liquid drains from the cone taken into the water basin, at what rate is the height of the water changing? What's it asking for? dH dt. They don't give us a specific time, but we're going to find we really don't need that because we're going to have a constant rate here. So when we take our derivative, we're going to get dV dt. 49 pi is just a constant, so we get 49 pi dH dt. And the rate that it is being drained from the tank, which was 5, is the rate that it's being added to the waste basin. So we would just plug in 5 over here, and that would be cubic feet per minute. And that's going to equal 49 pi . What's happening with units on this? Yes, because I should have put feet. Yes, 49 pi feet squared. I should have put feet when I plugged in seconds. DH. DT. Again, you can ignore the units till the end if you want. You don't have to do that. So if you divide by 49 pi square feet, you've got 5 over 49 pi, which, if you leave it, 5 over 49 pi is fine, or 5 divided by 49 pi is going to give us 0.032, and that's going to be, it's the same thing that happened over here. You got cubic feet per minute divided by square feet. So that is going to give you feet per minute here also for your DH, DT. And that will be positive because where the cone was being drained, this one is being filled up. So you'll have positive right there. All right, so we had not done that cylinder problem before, so I wanted to look at that because that's something different. It's actually easier because you can plug it in, but it might be something you weren't sure about since we haven't done one. We definitely haven't done one like D either, although I think it's a really cool concept as well. So water continues to drain from the conical tank into the water waste basin at a constant rate of 5 cubic feet per minute. A pump begins draining the waste basin at a rate that is determined by the equation d of t equals 5e to the 0.02 t minus 2t plus 1 cubic feet per minute. At t equals 5 is the amount of water in the waste basin increasing or decreasing. Explain your reasoning. What do you think? Do we need to take a derivative? What does D give us? Yeah, so a pump begins draining the waste basin at a rate that is determined by the equation here. So it was like D, even though it's not marked a derivative, it is the derivative because it's your rate. So, if we think about what's happening, we want to know whether or not the amount of water in here is increasing or decreasing. So if we got water coming in faster than it's leaving, then we would have the tank start to fill up, right? If it's coming in at a rate slower than it's leaving, if it's draining faster than it's leaving, it's going to drain, right? It's going to decrease. So really, we just need to think about the rate water enters the tank and rate water is leaving the tank right here at t equals 5. So water enters tank at a rate of, what's the rate the water's entering the tank? 5 cubic feet per minute. Right, that's just that constant rate we've been using for this problem. So water drains from tank at a rate of, how are we going to find that? Plug 5 into our equation. So D of 5 is going to be, this is calculator active, so you don't have to write down 5e to the 0.2 t. You don't have to write all that down. You could just type it in. 5e to the 0.2 times 5 minus 2 times 5 plus 1. And we get 4.59 141, and that'd be cubic feet per minute also. So, what's our conclusion? Is the amount of water in the waste basin increasing or decreasing? All right, so at t equals 5, the amount of water in the waste basin is increasing because D of 5 is less than 5 cubic feet per minute. And there's a lot of ways you could word that. You could word it that, water is entering the tank at a rate faster than it's leaving. You could word it a lot of ways. Mm-hmm. Oh, since we said tank instead of waste basin, I think we'd be okay, but probably, especially since you've got the conical tank, you might want to call it the waste basin in both places. That would be better. I think they would make the assumption that's what you meant there as a grader. I know I certainly would grading, but waste basin would be better if you use waste basin in all places because you do have the conical tank earlier. All right, questions? Gracious, we just don't have no time. Okay, let's see. What's going to be the best use of our time? What's going to be the best? All right, homework. You guys what did you guys have? 17, 18 were cone problems, right? 23. All right. Since we have just done a cone problem, I don't want to do 17 or 18. Although I will tell you that the answer for 18 is it's 9 over 10 pi, or that as a decimal is 0.286. So 18 should be 0.286 feet per minute. It's similar to these problems, so I don't want to rework another one there. 23 is a really good problem, and we need to look at it sometime, but it's a difficult problem, and I don't think our time will be best used looking at it right now. Then we had, 34, 35, 36. I like 34. It's a cool problem because, I know that whenever Todd was doing roadway design stuff, whenever he worked in Raleigh on the training program, they did, stuff for bank curves and stuff. So, this is, there's people out there, people that I know that are actually using that sort of stuff. Now, I'm not saying he was using calculus for it, but he was, they were using formulas like that and doing so. It's cool. What's not cool about it is it doesn't really, it's asking for something really general. It's not asking for a specific answer, if this curve has the radius of this and, what is our rate, what is the maximum speed limit you should put on this curve. So, if you were to, I don't think you're not going to see a banked curve problem, but if you were to see something like that, it would probably have more information you were plugging in. So I'm skipping that one too. 35 and 36 are a little bit similar. I think it might be helpful to look at one of those. Do you guys have a preference? 36. Let's look at 36. All right, so 36 gives you a picture there, and the answer for 36 also is, for A, you should get 1/2 radians per minute, B is 3/2, C is 1.87. It is fine for the homework, I don't care, but on my test and on AP exam, everything's always in radians. So, so you want to go with radians whenever you are looking at the test or the AP exam. And my tests, just because I use AP problems, are always going to be radians also. So our book doesn't do that, or well, our book did do that on this problem, but, and I'm not saying everybody does that in real life, but just because of the AP exam, that's the case. So I don't care, really, but know that on the test it'll be in radians. So, no, they'll just give you radians in the problem. The only possible thing maybe is if it were like a 90-degree angle sort of thing. They might tell you that this makes a 90-degree angle, and you have to, know that that would be pi over 2. But they're not going to give you like 30 degrees or 55 degrees and expect you to change it to radians. But there's a chance they may use that phrase 90 degree because they assume you will know how to deal with that pretty easily. So, airplane, here, we've got theta. We know this is 5 miles. That is not changing. It's flying at a constant altitude, so we can go ahead and label that there. And it is flying overhead, and the question says an airplane flies at altitude of 5 miles toward a point directly over an observer. The speed of the plane is 600 miles per hour. Find the rates at which the angle of elevation is changing when the angle is, and then ask for A, B, and C. We'll probably just look at A because it just changes what you plug in. But it's what is it asking for? What variable are we looking for? D theta dt. So we're finding d theta dt when theta equals 30 degrees for that first. It is weird. That is so weird that the book gave degrees in the problem and radians is the answer. I don't like that. Yeah. I would give the answer in degrees also for this, looking at it more closely. But the book gives the answer in radians, which is weird. They're not going to do that to you on the exam. They'll either, well, everything's going to be in radians. Whenever we look at that triangle, what kind of equation can we set up? We got to figure out really where the other variable is because we need another variable, right? So we call that x. That's good. So then we would be doing what? Trig function. Tangent theta equals 5 over x. And I would do this before I take the derivative. I'd write that as 5x to the negative 1. It'll make it much easier to take your derivative if you do that. And so if I take the derivative of tangent is secant squared theta equals negative 5 x to the negative 2 dx dt. Oh, yes. Thank you. I made a terrible mistake there. Because we're going to be in trouble. We can't find d theta dt if we don't have a d theta dt. So, secant squared theta d theta dt. Alright, and I know theta is 30 degrees. Let's do pi over 6 because they did give us radians. So let's do pi over 6. So secant squared of pi over 6. I don't want to replace d theta dt because that's what I'm trying to find. Oh, I don't have x. How can I find it? If I know, I'm looking at the point where this is pi over 6. So I could just use trig to find that, right? So I could say tangent of pi over 6 equals 5 over x. See, tangent of pi over 6. Right here, this is root 3 over 2, 1/2. Sine over cosine. One over root 3 is 5 over x. Oops, what's it doing? It's going crazy. Why is it not? Well, I was doing Control C. That usually works, but where's my undo? It's making it worse. Let's redo. Look, it's. Alright. Maybe we can. Alright, so that's going to be x equals 5 root 3. Right there. So, and if we want to use the calculator, that's fine. 5 root 3. In fact, I'm going to use the calculator here in a second. It's negative 2 because I don't want to deal with that. And then, what's dx dt? It is negative 600. Because that is the speed the plane is moving. So that is also going to shorten up this distance of the bottom of that triangle as it moves. If we resort to the calculator, 1 over cosine of pi over 6. And then we got to square that, is 4/3. D theta dt. And then we're going to put all this other stuff in here. Negative 5 times 5 root 3 to the negative 2 times negative 600 is 40. So if we multiply both sides by 3/4 d. Why am I? Why does it say the answer is 1/2 and I'm getting 30? I used radians though, didn't I? Oh, the book is stupid. The book gives the answer as 1/2 radians per minute. Did it tell us we had to give radians per minute? It did not. But we plugged in over here. This is 600 miles per hour. So our answer is 30 radians per hour, which is 1/2 radians per minute. Because in a whole hour, 60 minutes, why did they do that? I mean, I know why they did it, because you care more about like what's happening quickly, but still. They didn't specifically say we had to have radians per minute. And then we're not going to go back and redo this, but for part B and part C, you would just put in 60 degrees and 75 degrees instead for those. All right. Time is so short. Well, let's look at that test review. Well, that's freak out stuff. Let's go over here to your stuff. Let me see if there's one we need to look at. There's some things I need to remind you of. Specifically, there's one I know that is on there that you need to be reminded of. Okay, look at number 1. This one's a calculator active problem. For what values of t is the speed of the particle increasing? Speed increasing. Okay, we did some speed increasing or two problem, but it's a little bit confusing. For speed to be increasing, remember speed is not velocity. A lot of times you just want to look at acceleration and see whether or not it's positive or negative. That's not exactly right. Okay, for speed increasing, velocity and acceleration have the same sign. Okay, so that could be positive velocity, positive acceleration, which is the way we normally think of it, or it could be negative velocity, negative acceleration. It doesn't ask for it for this problem, but if you have speed decreasing, then velocity and acceleration have different signs. So I'm not going to do this problem, but they give me the velocity formula, right? So I can graph that in the calculator. What am I looking for when I look at that velocity? I need to have velocity being positive and acceleration being positive, or I need to have velocity negative and acceleration being negative for my speed to be increasing. So I can tell velocity is positive when it's above the x-axis and negative whenever it's below x-axis. To avoid having to look at the second derivative, if my acceleration is positive, what does it tell me about velocity? Increasing. And if my acceleration is negative, I would be decreasing. So you're looking for the parts on your graph where velocity is above the x-axis and increasing, or where it's below the x-axis and decreasing. Correct. You could look at the derivative, but you don't even really have to look at the derivative for this one. You could just graph velocity, and you're looking for those increments where you're positive and increasing. So you could find like your 0, like say it looks like this. Yeah, I don't know what it looks like, but say it looks something like that. You would be positive and increasing on this section right here. So that would be one of your answers. You would be negative and decreasing right here, and then you'd be positive and increasing here. So those 3 sections I've marked would be your answer. So you'd find those from your graph. And you can look at a second derivative, but you don't have to. So I know I put a speed problem on there. Speed increasing or decreasing. I can't remember which one it was, but there's one on there. I can't remember if it's calculator active or not. If it has a graph, I can't remember. I know it's on there, so watch out for it. Let's see. Don't do 6. Okay, here's one that, again, I'm not going to do. I just want to remind you what you have to do. Particle moves along the y-axis so that t is greater than 0. Its position is given by this formula. At what time is the particle at rest? What are you looking for there if the particle is at rest? If you are at rest, what can you say about your either position, velocity, or acceleration? Velocity is 0. All right. So if the particle is at rest, that means velocity equals 0. I may actually go ahead and do this one. How do we find velocity? Y prime of t would be our velocity. And so that would just be 3t squared minus 15t plus 12. And we would want to know where that's equal to 0. So I divide everything by 3 to give you smaller numbers to work with here. T squared minus 5t plus 4 will be 0. So you'll have t minus 4. T minus 1, and so you'll get t equals 4 and t equals 1. So the particle, that should say at what times is the particle at rest. So you would say t equals 1 and t equals 4 would be your answer to the question. So if you see particle at rest, that's velocity equal to 0. It's been a little while since we looked at that stuff. Questions on that? Oh, wait. I told you to mark out 11, but you can do 11. You may see something like 11. It's a quick problem. You don't have to show work on that. So you can do 11. I was wrong. But don't do 12, 13, 14. There. Okay, so the key for these are up. It basically leaves that second FRQ and that handful of questions there for you to look at. I will be here Monday for Smart Breakfast, Lord willing. So come by if you have questions. We'll take our test Monday. If anybody needs to, there'll be an exam Tuesday. I'll email you if you need to take it. And then we'll move on to next semester.